and can you see my MATLAB screen?
Yes.
Okay, very good. Let's see it. All right, so the next hour or so, we're going to go over some of the wrappers around GMT, which allows you to get to GMT from other environments, basically. I'm going to go through MATLAB or Octave, depending, Python and Julia. So I'll start here and showing you, so the oldest wrapper was GMT Max Toolbox, which Joachim and I put together back in 2017, I think. And in doing so, we learned a whole lot about the GMT API and issues, which has benefited the other wrappers that come since then. But if you do a lot of work in MATLAB, then having access to GMT from MATLAB may be of interest to you. So we're just going to look at some simple cases here where I'm mostly going to focus on using GMT as a calculator, sort of opposite of what you might think, and then let MATLAB plot things. And I'm doing this because we have a couple of regressions in the toolbox that I couldn't get to work right now. So I'm just going to do some basic things. Here we have a live script in MATLAB, sort of like a notebook. The first example here in section 1 is to use GMT to do some filtering. We're going to do basically a 1D filtering using filter 1D. It's a GMT module. You can see here in the first box here how we call GMT. We pass the module name and then the options. And then because we're in MATLAB, we already read the data file in here, raw data, and I'm passing that as an argument to the GMT function, and out comes another data set, which is the filter value. And then I'm just doing basic plotting of this data set and the filter data set in MATLAB. So, oh boy, can I get rid of that there so I can get to my buttons? Okay, so I'm going to run the first section here. And you should see on the right here, we have a basic MATLAB plot of the raw data, the blue line, and then the red filter data that came back to us from GMT. So it's pretty easy if you want to call on certain functions that may not be available in MATLAB, but have been coded in GMT to do that in your MATLAB workflow. The second example is going to be a 2D gridding case. So GMT has a lot of algorithms for gridding data that is basically XY coordinates in the plane, randomly distributed with a Z value. And turning that data set into something that's regular, like an image or a grid, requires this operation as 2D interpolation. And GMT is very good at that. It started out doing a lot of these things. So there are many different algorithms. The one I'm going to show off here is a spline intention in 2D. It uses the Green's function for a 2D spline intention to come up with the solution that exactly fits the data. So again, the data here is being read in from a data table, depths.txt. I get a data set in memory. I'm then running green spline, which is the module I'm going to use with typical GMT arguments that sets the operation, specifying a spline intention over a distance of 0.3. Oh, sorry, with tension of 0.3. And I'm passing in the depths, and back out comes the GMT grid. And then I'm going to contour that grid in MATLAB. We'll see how that goes. All right, so here we have that plane figure with the data points as stars and the contours here. So if we look at the grid here called G, you can see the grid has all the typical information you might find running GRD info. You know, the dimension 81 by 71. Here's the command that was run. It has X, Y, and Z data. You can get to these. These are basically a structure. So gmt.x will give you the X coordinates, for instance, which we used here to pass into the MATLAB function that does the contouring. So it's pretty easy to call GMT from MATLAB. and using structures and matrices and what have you in memory and pass in and out of the GMT functions. Again, I'm just doing a small subset here. I'm probably going to be done before 20 minutes is up, which is fine. It's, I'm more curious to look at the Julia and the Python myself. All right, spatial analysis. So GMT has a lot of algorithms that are hidden within many modules. And some of those things are difficult to reproduce in MATLAB without some extensive coding. For instance, here we have a data set, a polygon data set, and we have a bunch of points. And we want to find which points are inside this polygon, because you may want to treat those differently or exclude them or exclude stuff that is not inside the polygon. So I'm using GMT's GMT Select function that takes a polygon, and I'm passing in the polygon on the data file, and back out comes the array that shows me which points are actually inside. So then I can plot all the points and I'll plot the polygon, all the points, and the inside points in green, and we should see that this actually works. So running this section. Where'd it go? They did not run it. Run section. There we go. I don't know what happened. All right. So here we have the plot. We have the polygon. You can see all the points have been plotted, but the ones that are inside have been plotted a second time using green. And you can see it works pretty well. This works also on the surface of the Earth, where we are aware of polar caps and poles and all that nastiness that very often GIS packages will fail at, because they're all sort of Cartesian at heart. But the GMT is spherical at heart, basically, so it has some advantages there. Let's see here, advanced math. Okay, well, one person's advanced math is another person's trivia, right? So I don't know if that's a good title, but GMT actually said MATLAB and Python and Julia and similar environments, of course, they are great at doing calculations on tables and matrices and vectors and so on. That's why it's appealing to use GMT within those environments. But they don't have everything coded up without you adding a lot of extensions. So GMT has access to several hundred different functions. Some of them are just, basic math, which you probably can do in the other environments. But some of them are very specific, like compute spherical distances from a point to all other points in the grid, or find the distance to the nearest coastline. These things are built into the tools GRD math and GMT math for tables. And here we're just going to look at, computing the K function, the Kelvin-Bessel function K here on a grid from -4 to +4 in both X and Y. And we're just computing the distance from the origin to all the points on the grid, and a value, that's the radius from 0, 0. And we're going to evaluate the K function with GRD math. Back comes the grid. We then compute cosine of X, basically, that's another grid. And then we multiply those two grids together using GRD math. And then we're going to draw a figure to show what that looks like. And there it is. So that's a 3D surface of the result of that calculation. See if I can, oops, there we go. I can do things like, explore. Oh, I see these two little bumps here because I did the cosine. We can explore that figure a little bit. Right, I'm doing okay with time here. So as I mentioned, GMT has a lot of gridding functionality built in. And one of the early reasons for GMT was actually to handle large data sets of longitude, latitude, and bathymetry or gravity or magnetics on a global scale, and handle the fact that you can't necessarily use all the data everywhere because of aliasing. So we had to spatially reduce the data sets with block mean or block median or block mode, even for some topography, So it's a very standard workflow to take a very large data set, run block median to decimate it down so that there's only one point per node in the grid that we're trying to make, and then run surface on this. So for instance, the 15 arcsecond global topography data that you heard of, which is in the Earth Relief, which is made by Dave Sandoval and colleagues, that is a giant gridding function reducing, almost 500 million data points on a very large grid, and that's done with block mean and surface. So here I'm reading in longitude, latitude, and data from some ship cruises near south of the Hawaiian Islands, near the geologists' seamounts. I'm running block median on the data we read, and then I'm running surface on a 1 by 1 minute grid here, all calling GMT functions, passing back data sets and grids. And then I'm just going to make a plot of the data and a surface of that data. So let's see if that works. Oh, there we go. So the top portion here in subplot is just the data distribution and a contour map. So you can sort of, a little small here, but you can see the contours of the geologist seamounts. And here's the data distribution. And here's the surface plot of, again, of that 2D surface. And we can sort of zoom around here and look at the seamounts that we have gridded in this little script. So it's very simple to do GMT from MATLAB. You can pass things in and out. You can also read files, obviously, like we did here. We read in a file into memory first before we pass it to block mean. And grids, it understands grids in and out. It's pretty easy. And with the structure, we can get to the Z and X and Y and the various members of the grid. All right, grid sampling. So often when you have a grid, you make maps and contour maps and things, but to really understand your data set, you may actually want to look at profiles, cross-section along the grid, because it's kind of hard to look at variations just based on contours or colors. It's hard to translate colors into some information in your brain. So here we're going to look at the pretty common application of this. We have a grid near Japan here, japan.nc, and I have digitized the trace of the Japan trench, basically, which is arcuate. And I want to create a bunch of profiles normal to that trench. So they're going to swing around, but always be locally normal, and sample the grid. And then I'm going to stack all these profiles together on a common XY plot and examine them and look at the variation around that stacked mean profile. So this is a job for GRD track, which will take one or many grids and can automatically create these swaths, basically, or this cluster of lines that you want to sample the grid along. And then I'm just getting that back and plotting them in MATLAB using basic MATLAB tools. So here you see all the individual profiles that are crossing the Japan trench. And then the stacked one is in bold there. And they all, they're pretty common. They all have the same basic shape of the flexural signal on the right here as the underwriting plate coming into the subduction zone. So that's pretty standard GMT processing. And then we have supplements, right? So we've used a couple of supplements in this workshop. We looked at the size supplement that Dangdang showed us, where we looked at plotting beach balls and cross sections, and we can even plot seismograms and a variety of things that we didn't get to. And Eric took us through some of the geodesy tools, particularly PS Velo, for plotting these GPS or GNSS velocity vectors. There's many other supplements that deal with specific aspects of science. Here's one that is sort of a little bit more general in that it doesn't really pertain to a particular scientific discipline, but it's a tool, X2Sys, that analyzes intersecting tracks. be it from ships crossing the ocean to satellites spinning around the Earth or other planets. And when these tracks intersect, you would expect that the measurement that they made along those two intersecting tracks should agree at the intersection. And of course, that is not true, because there are noise and there's drift of instruments and there's navigation issues. So it's very helpful to look at intersections between such data and try to tease out some systematic errors from the crossovers so that you can adjust it and optimize the data before you throw it into a gridder, for instance. Otherwise, you get all kinds of artifacts in the gridded solution. So here we're going to use X2Sys on a bunch of tracks. I'm not going to go through all the lines here, but basically we take all these tracks, we compute all the crossings, we're plotting up the crossings, we look at the difference in measurements at all the crossings, and I am somewhere in here, I do a find command to find all the bad tracks which have crossings values more than 4. So we know where they are. So I'm going to run this section here. Somewhere, did it not take run section? No. What's happening? I ran this earlier. Dear, what is it talking about? There. I'm sorry. I'm laughing because I ran this several times earlier today. And now it is going to tell me that there is no such module not found. Brilliant. Okay. Well, I'm sorry, but that part didn't work.
Well, time for a GMT destroy.
Was that?
And time for a GMT destroy and try again.
Retry that. It's pretty funny. It's funny because I've done this so many times today. But no, it's not gonna let it happen. All right. Well, we'll figure it out later. Anyway, what you would have seen is a bunch of lines in the plane that are intersecting, and it would have identified the coordinates, the intersections of all of them. And then the ones that have a mismatch of more than 4 in the Z direction would have a circle around them. And then there will be a little histogram showing the distribution of these errors. So you can get a sense if they're outliers or if they all just sort of cluster around a Gaussian distribution centered on 0 or centered on some other value. Anyway, so that's really my demo here. In terms of you using GMT Max on your system, if you are running Windows, I believe it is already installed in the Windows installer, so you're good to go. If you're doing Macs or Linux, there's more work because the way MATLAB is installed on computers, it comes with a whole bunch of software that it needs that are shared, like NetCDF libraries and so on, that GMT also ships. But unfortunately, their versions tend to be older. And because it is the MATLAB application we're calling GMT, sometimes it seems to be calling the wrong library. So we haven't quite cracked the nut of how to do this there. I know how to do it on the Mac. Obviously, I'm running the Mac here, but it's a little ugly recipe. So if you're interested in using MATLAB and GMT, you should contact us on the forum or on the GitHub page, and we're happy to help you since this is kind of moving target. All right, I think I'll stop there. It's the stop my share here and pass the baton, I guess, to who's next? Is it Joachim or Max?
Max,
in the schedule, I can go.
Max.
Okay.
So in this section, we'll be talking about the Python wrapper for GMT, PyGMT. PyGMT was started in roughly 2017 by Paul and Leo. And since then, it's expanded greatly. So we've had new people come involved over the years. In particular, when Leo was finishing up his postdoc, Dong and Weiji got involved and were really instrumental in making sure GMT or PyGMT continued to thrive during that transitional period. And now we've had many more people get involved in PyGMT development. We have, I think, 6 developers, and we have many, many contributors. So it's a really fun project to work on. If anyone's interested in getting involved in development, I encourage you to get in touch, but it's also a really useful tool to just use in your own research. And that's what we'll be covering here in this demo. So the main reason why you might want to use PyGMT is to access GMT's functionality directly from Python. In particular, if you have tools in the scientific Python ecosystem that you like to use for your research, could be OBSPy or say X-ray, that would be useful to have integrated with some of these features that you've learned from GMT during this short course. PyGMT is a nice interface that enables that. In addition, we try to make PyGMT more accessible by having longer form options for all those one-letter options that you've had for GMT. But note that those longer options will be coming to command line GMT in future releases as well. And as you'll see here, we also encourage use of PyGMT through interactive development environments such as Jupyter Notebook. So that's what you see here, Jupyter Notebook, where I will be showing the same examples that you saw throughout this short course through using command line GMT, and then a Python example of it. So this is so that you can see kind of directly translated how you would do this in Python. That said, the optimal design of a set of code in Bash scripting is not necessarily the same as what it would be in a Pythonic way. So in your research, if you're starting from scratch, you'd probably want to design your Python modules a bit differently. But if you're just translating from a Bash script, this will hopefully provide some useful information. If you want to learn more about how to use PyGMT in kind of a Pythonic way, integrated with all these other Python packages, we have a pretty extensive documentation. So this is pygmt.org, where all of our documentation is hosted. And in particular, we have tutorials for various tasks, as well as a gallery example that shows a little bit more granular examples. For example, if you in particular want to plot roads stored as GeoJSON or a different type of geospatial file that can be read through GeoPandas, you can look at the roads gallery example. And lastly, we also have links to our external resources, including a short course that we very recently put together for EGU. So this is about 90-minute introduction to PyGMT, where you can learn about basics, how to integrate it with other scientific Python packages, and then some specific use cases like planetary science and LiDAR processing. But in this demo, we'll just see how you could do these same examples that you've seen in Python. So we'll just start by importing the PyGMT library. Every function and method in PyGMT can be, or every public function and method can be accessed through this top level library. So you shouldn't need to import any other modules to work with PyGMT. And this is just a IPython class that will be used to display the bash output. So here we have the first example. This is from the basics section of this short course, and we're creating our first map of Italy. So you will probably remember that. We have this coastline image with the country plotted and an inset map. If we wanted to do this in Python through PyGMT, the first step for plotting with PyGMT is to create an instance of the figure class. So this fig equals pygmt.figure is serving the same purpose as what you saw earlier with the GMT begin, GMT end, or GMT figure structure. So this automatically handles all your sessions and figure control for you if you create an instance of the figure class, and then you call the plotting methods through this class. So for example, now that you have a figure created, you can call fig.coast with the same options as from that first example, but rather than using -r, you can use the long form options. So for example, region is -r, And you can either pass in a string, like for example, for shorelines, have the string be thin for a thin pen specification, or you can have other formats. For example, for a series of items like region, where you'd have 5-20-35-50, you can now pass in a list or a 1D array. And likewise, for parameters for GMT that you would not pass an argument for, you could do a Boolean true. So this would be equivalent to -b without any arguments. So frame equals true to plot an automatic frame. The second thing to note here is that throughout PyGMT, we often use context managers. And this is something that will automatically set up and destroy a particular set of configurations or a portion of your map. So for example, this context manager with fig.inset is automatically managing that GMT inset begin and GMT inset end, such that all the code within this context manager will be applied to your inset. So if we run this code, we can see that the output's the same. And this is really one of the main points to get from this demo, is that the vast majority of capabilities that are available through GMT are also available through PyGMT, and with the added benefit of having access to other Python functionality. So moving on, we have Joachim's lines and symbols example. In the interest of time, I have only replicated the lines portion of lines and symbols. So here we have the output from this bash shell. And to translate this to Python, rather than appending to a file, we can create a 1D array for our X and Y data. And then in addition to passing a file to our fig.plot or fig.grdimage functions or methods, we can instead pass the data that's stored in memory in Python directly. So you don't have to create an intermediate file. We, for tabular data, accept NumPy, ND arrays, and pandas data frames. If it's geospatial, you can also do pandas geodata frames. And similarly, as you've seen before, we have the long form aliases for each of the GMT arguments. And in cases where you would do, say, -b multiple times, instead you pass a list of the different arguments to -b. So this is the equivalent of -b AF space -b west, south, east, north. And again, you can see that for managing configurations, we have a context manager. So all of the code that's within this context manager will have this configuration setting it. So here we have PS line cap round for one line of Python code, and here we have it applied to 3 lines. And I took a little bit of a shortcut here with not doing a PS text call, but that is possible as well. Moving on to the grids example. So this is Federico's exercise 5 with a relief map of Argentina. It might take a second to do the contouring and loading of the data set, but we can do this very easily in Python as well. And one thing to note, so this is using the same remote file mechanism, but through PyGMT, you can also actually load in the Earth SynBath or Earth relief data as an X-array data array. So that would allow you to manipulate it and engage with it in other ways as well before doing the plotting. So that might be useful rather than passing a file name to GRD image. You could pass a X-array data array. For the seismology section, we have 2 figures created. We have a mecha figure and a coop figure. So this is the Bash example. And in the Python example for mecha, you can notice that we have passed in a file name here, although you could also pass in a different other in-memory Python objects to Mecha. And rather than using -s, we have split that up into multiple arguments. So this is a form of trying to simplify the GMT syntax in cases, because we have, by using long format options, a lot more available to us rather than just 26 capital letters and 26 lowercase letters. So in cases, you may see a single GMT option split into multiple PyGMT parameters. And this type of API design for PyGMT is something that we're working on expanding to make things even simpler, and something that we're actively looking for feedback on. So if you see a part of PyGMT that you find particularly intuitive or particularly difficult, either raising an issue in GitHub or posting on the GMT forum would be really helpful to us. So in the COOP example, it's a bit different. So we're in the process of wrapping all of GMT's modules in Python, but we're not there yet. So COOP is one example of a GMT module that we actually don't have wrapped yet, but we can still access it through PyGMT by using the clib session class. And so that gives us access to call any module that doesn't already have a high level access through PyGMT. So even if you stumble upon something that's not already implemented, you could work around that in this way. The alternative, which would be even more helpful, would be to help build GMT or PyGMT. Wrapping a module is actually not all that difficult, and we have a lot of people who would be willing to help you with it. So if you come across a module like that you really need, like COOP, and don't see it already in the library, post an issue requesting it, or even better, try to help. So this is the second example from the Seismology page, and then the last section is the geodesy section. So here we have a subset of that make maps figure from the geodesy section, and output as a PNG file. All of the capabilities from that section are already available in PyGMT, and here you can see one small example of using in-memory objects rather than reading and writing ASCII files. So here, whereas the original script had the output from GRD sample to go into an ASCII file, we output it and store it as a pandas data frame. And in doing that, rather than using awk, we can use pandas concat to create the format that's required for Velo. So it's just one example of how having the data stored in memory so that you can use different manipulation tools can be simplifying compared to some of the more complex bash utilities. So hopefully, as part of this demo, you've seen that PyGMT has a lot of capabilities. It may be able to help you with your research. And I want you to remember that we'd really enjoy to have more people become involved in PyGMT, either as users or developers. And the ways to get involved are through the GMT forum, through our community meetings that are held quarterly, or through GitHub. And you can comment on any one of the documentation issues, the feature issues, whatever is exciting to you. So thanks, and hope to see you around.
All right, very good. Nice. And that reminds me, Max make a very good point here about the community. The lowest level of interaction you can do is to point out a problem, right? To just say, that doesn't work, something, instead of just saying, it doesn't work, I'm not going to use it, because we can't fix problems you aren't aware of, right? So helping us finding problems and weaknesses allows us to tackle them. So that's really important that you become part of the community, sign up to be on the forum. It's a useful resource. both ways. You can learn from it and you can help others and you can help us. All right, thanks. So I guess I'll just, in the interest of time, move on to Joachim, who's going to show us Julia from his iPad, right, Joachim, from your iPad?
No.
Oh, no.
No, not iPad this time. No, would be too risky. No. Actually, I could do it but remotely and things like that.
Maybe next time.
Maybe next time. No, not these. Okay, I have to share screen. Yes. Share screen. Okay. So a little bit of history, but not spending too much time on these. Julia, maybe not of you know about Julia. It's a less well-known language or environment, but is a very powerful one that has very particularly capabilities that allowed me to port GMT to Julia. And it's, well, I would say it's the entire GMT that is available through Julia. It actually is a continuation of the Max work. So everything Paul showed you, although it was in small letters, can be run on Julia with one single change. Is to replace the quotes, the single quotes that are used to define text strings in MATLAB. On Julia, they use double quotes. So if you replace single quotes by double quotes, you can run the Max examples in Julia as well. Well, that's how it started, but then it kept evolving because more challenges came up and I wanted to make it easier to use. So I've been working in a new manual that is linked on the GitHub example page and on the gmt.gl page. It has a lot of examples there that I will come here if I use all my material and I need something more for it. But meanwhile, yesterday I also tried and experimented with the notebooks in the Visual Studio Code. And it turns out that it's very handy and simple to use. So you type code, you select, like in Jupyter on the browser, you select cells that are code and cells that are text, and you execute them. So a bit similar to what well, very similar in fact to the PyGMT case. You start using it by loading the package. And you do that by issuing this command using GMT, which when we run, oh no. Okay, I should have thought on this before. I have to relaunch, otherwise it would be very, where is it? It's the kernel. Where is the kernel? Restart. Does not want to restart. It's spoiling my surprise. Okay. Well, I have to resort to another solution, but why is this? Oh, it's running. No error. Okay. Okay, maybe it did restart. Let me try it again. Okay, so it ran. I'll do it again. No, it did not run. No. Okay, I cannot spend all the time in here. Okay, I have to run copy paste commands in another Julia session instead of using that fancy thing. So this first command uses the download mechanism and will extract a bit of the Earth relief at 5 minutes resolution in a region that is corresponds to Atlantic Ocean. Well, we had some problems with also a regression that you cannot spell the name of Atlantic Ocean, you have to use the code for it. And G, like we'll show it in MATLAB, G is a kind of a structure that has the header more than it is used here and the array. So we have the grid in memory. In fact, no. Okay, that is fine. In fact, this grid in Julia allows us to do more than in the other language, I think. I can do, for example, multiplications. I can have, I'll do it, G2 equals G plus 10,000 because, and take the S square root of it, it's QRT, I see that, or just some calculations, and I have a new grid. So you see, we can do any calculations we want just using the variable name and with the added bonus that is not creating intermediate array. So if you have a long calculation and with a long grid is not using memory for each of the intermediate steps. This makes it very powerful to do calculations. But coming back to the G grid, really annoying that. So there are handy commands in Julia, in the GMT port that expands on GMT. So all the GMT options and modifiers and flags have received extended name. For example, -G is proj or project, CMAP is -C, shade is -I on the GRD image. And this model EN show joins all of them and lets us do the image with a guessing a projection, adding a coastline and a color bar. Oh, thanks. So see, with a single command, we have these. Some facts about Julia. Julia is known to be very fast, but it's also compiled on real time. So the first time you run commands, it might take some time. The latency is a bit big and makes it look slow, when in fact, is, for example, this case, he had to compile GRD image, ES coast, color bar, and maybe others. So, but you see, with a single command, we have our nice map where the projection, which I think is a conic projection, was guessed given the region extents. We have the coastlines and we have the color bar. Like these short ones do not give much power on controlling the details, but we could have done it if instead of just saying coast equal true, you would have specified what type of coasts we wanted with a long list of options. So that image show. So, but that one was a single command. I like it very much. The one-liners, when they are enough to do what we want. But many times, then they are not enough. If you want to add more elements to the figure, you need to split it in commands like in the regular GMT or PyGMT. So I'm going to split that one in these parts, calling this time the GRD image with the same arguments, proj equals guess, the same color scale, saying to do automatic illumination, coast bars, color bar. But this one, it will not show anything. Okay, it finished, no error, no message, immediate work, but it didn't show anything. In fact, EM show is a particular one that it is made to show the result at the end. All the others, they will keep adding to the PostScript file, like the regular GMT, because this is what it is, until we tell it to display the figure. So I can do things, I will add elements. It's in here. Oh, yeah. Oh, it's not, I'm going to have an, or maybe not. I'm going to read a small shapefile directly with GMT. Yes. And inside a zip file. That is, you can read shapefiles directly in the zip file without even have to decompress it. And it generates an element that we will talk later, a data set with the contents of this shapefile. And we can add it. I'll add it to the plot. But again, there is no show command. Just plot. You have to compile plot. And now I'm going to have a focal mechanism. See, just an example. Here again, sorry, we had a little regression. And when we send the data in memory, like it is done here, the offset option, which is that option that plots the focal mechanism, not on its location, but on the location that we give it, which in this case is indicated by these two numbers, is not working when we use in-memory data. I thought we had fixed this bug, but it came back again. So as a result, I have to save it in file. This is what this command do. GMT write. He writes on his data set on the file, and then we can call it. E and the mouse. Oh, another thing I see. Because we are continuing to work on layers, the first command is a command name, and the other ones, the notation is the following. Add an exclamation mark when we keep adding to the plot. So we had plot, exclamation mark, mecha, exclamation mark. It means he's adding to an existing plot, and we are about to finish, yes, or this one. And in the last one, I'm going to add that little volcano that I like very much. And this time there is a show command here at the end. Show equals true. So it should finish the plot and display it. Okay, and here we have it. So we have the same grid, shade illuminated with ghost lines, with a color bar, with the maritime boundaries that were read from the shapefile, a focal mechanism offset from this location here, and a little volcano. So see, that's, well, the way it works is similar because, again, this is GMT only, but the focus has been done, has been applied to make long options for all the options and flags and whatever. For example, I have here marker where you say it's a custom symbol, the volcano, and we say the size, and we say the ML is short for marker line, which I could have spelled it as marker line as well. You say paint it with red, use fill, and at the end is show. So there is all of that new vocabulary to use GMT that makes it also a bit, well, not a bit more than that, hard to document because it's really a lot of new things. Imagine all of those multiple sub-options and sub-options of the GMT, all of them got an expanded name, and now you have to have a syntax for it and document it. And that part of the documentation is not even half done. So using Max words and Paul, all the help that we can have using and expanding the documentation is really, really more than welcome. So what's the time? Yeah. Let's change the subject. There is one model in in GMT that is Earth tide that calculates tides. Well, I have seen that many people got surprises when they were told that Earth, the solid Earth, also has tides. It's not only the ocean. And the tides in solid ocean and solid Earth are not that small. They can go from peak to trough. That can go at 30 to 50 centimeters in one day. So we can calculate the Earth tide. So the model is called Earth tide. Here I had G, but I could have as range. So we tell it the date and compute G. No. So this is one warning that keeps coming. And I can show, you can see, again, it's only a grid. You want to make a single image. So I do EM show. The name was copied from MATLAB, where again, we say grid, coasts, color bar, title. Oh yes, no guessing the projection. So it's a linear projection, and we have the tide for the day of today, and you see here with the color bar that it goes to 20 centimeters. This is meters to minus 14 centimeters. So this is not such a small deformation of Earth, and we can calculate it with the Earth tide in GMT. Show. Okay, but we can also plot time series. The Earth tide model let us compute grids or a time series for a certain period and a certain location of Earth. So I have to copy them one by one. Now I will talk a little bit about this D. No, it was. Yeah, I want to talk a little. So calculating the time series, and here's result. And well, like the Max, also the Julia wrapper has a couple of types that are very important and very well important to understand what you can do with them. And this one is a table, but a table that can come with column names. Well, people that know about data frames, it looks like, but this is not a data frame. Data frames is like, well, what? I mean, there you can do much more thing with them that we can do with these in terms of databases. So it's more akin to a database, and this one is just a table with the same data type, but with things like data, the type, the geometry. We know if it's points, if it is a string, if it is a polygon, if it is 2D, if it is 3D. Yes, attach it a georeferencing information, and all of that can be used in GMT models or GMT rapid models, plus some functions that extend the GMT functionality. For example, we have here the column names, and I can address to them instead of saying that I want second column, third column by its name. So that's what this one does. So first one. Again, there is a plot, there is no show, so we don't see anything, but notice, we call it with D and the time column and the vertical component. And with the LC stands for line color, which you could expand it as line color or use as LC. LW, it means line width of 1 point, and a title. So it doesn't show up until we tell it to do so. I'm going to plot the other two components with different colors and legends and legend entry. So at the end, and with that, have the plots series. And here you see. So we have the vertical component, which is the highest one. It's normal. One is on the line of sun and earth and moon. And you also have the other two horizontal components, all three in the same graph, because we kept adding to the same plot and adding label entries, and at the end you have these. So you can do these with either a file name or an array that we can create with the language or import from the file, or whatever. What's the last one? Oh, this one is the same type of example, but expanded. There was 1 day. This is that will be 1 month. And because it's a single one, so we have time, vertical, color blue, legend is vertical, title, you spell title, and show, and the Julia wrapper uses a little bit different assumptions sometimes. So for example, if you don't say anything, he automatically picks annotations and ticks. If you don't want to, when we don't want to plot the frame, sorry, you have to explicitly tell it frame equals none. So say, no, I don't want a frame, because by default, it assumes some defaults and puts a frame. In this case, it even could find that one of the columns, the first column, was a time column, which GMT converted to a number of seconds with respect to the reference date. And it detected that it's a time column, and it made the annotations in time instead of those millions of seconds. So I think in question of time, I should be close. Let me, yeah, that's good. So that was it. As you see, there is all the wrappers, all the models are wrapped, except for the supplements. And those that are not wrapped can be called like in the MATLAB way. So all of them are accessible. Not all the models are documented. That is the big issue. So there's one place where we need contributions is on the helping the documentation, which is not so funny by itself. It's a little more funny if you do something and you want to know how to do it, and you have to dig into GMT, pure GMT documentation on how to do it. Then you can help with the contributions or expand the Julia wrapper that still has a lot of things to do. There are many models who were expanded and so on. As I said at the beginning, you can give a quick look on the oh, where is that one? This thing with the zoom tabs hiding things. Okay, the manual has a lot of them. Projections, you have all the projections, and how we do it in this expanded way. I'm taking more time than I have. So see, to do this map, you have to type a bit more than you have to do with the regular GMT. But on the other hand, when you read it, that is a big advantage. When you read this, and that is the idea behind all of this development, is that when you read the command, you immediately understand what it does, which we have to confess is not the case when we read a pure hard GMT script. Okay, so I will end here, and I'll be happy to answer questions and examples in our other forums and the GitHub's places. Okay, thank you.
Thanks a lot, Joachim. It's very interesting. All right, so we stuck to the 1 hour. That's pretty good. We all managed to squeeze in about 20 minutes. So I think this is a good time to take a 10-minute break before we get back and work on projects. If you have any questions or interest in any of the wrappers, you know how to contact us on the forum or GitHub and follow up. It is the future of GMT to use GMT from various wrappers, I think. And we need help of people trying it and reporting issues and helping document and helping wrap and the whole 9 yards, basically. All right, so let's set a 10-minute clock and then we come back again.
Just need to Joachim to stop sharing his screen.
Oh, yeah.
Yeah.
I'm still fighting with that.
I see that.
Thing that.
No worries.
Of my surprise. Yeah, I was so happy with it.
Clean back from the break, hopefully. Let's see. So according to the schedule, we are going to continue working on projects for as long as, oh goodness, 75 minutes, something like that. So we will be around. I think we changed the breakout rooms down to, let's see, wait to see, geodesy, seismology. How are we doing with the breakout rooms, Melissa?
We should be ready to go. There's 4 rooms. The grids, the images, lines, and symbols have both been combined into one. So there'll be 4 rooms.
And the seismology, since we lost Dong Dong, we don't have a replacement seismologist, I guess.
We can make a tour there. The simple things I remember, the other ones I don't.
Yeah.
And of course, if what? Where is it? Oh, you are sharing. Can I? If I share, okay, yeah, I'm sharing. Of course, it start working.
Yeah, it could start working.
There we go. I see something.
So it runs inside the Visual Studio Code. Okay, yeah. All right.
Max, around, yeah. I have a question, a doubt on this. I do not know how to control the width of the figures. They are as wide as the window, as the VS Code window. That is very big. This is not nice, because another handy thing is you can save it in HTML and you have directly something you can single file that you can transmit, but it makes it very big. This is huge. I don't like these big figures like that. I see all the others. I don't know why I have them. For example, the example that Max showed, that little figures that look nice. I really hate these very large.
What do you use? So we use IPython's tools for displaying.
It's the same. This is IPython. If I do it on the browser, I get the same thing.
Yeah, you have to pass a width argument. I'll send you a message describing how we do that. But we have in Fig show, there's a width for what will get displayed in the Jupyter notebooks. And we have a default 500, which is probably smaller than what the native default is. So that is what you'd want to probably.
I don't know. I know how to include a figure, and there I know that I can set the width equal 50% or the width in pixels. But these ones are displayed directly. So I generate and they pop up. The same thing when you do it in Python, I think. So there is no place here for me to tell the width of the displayed figure. That's the part that I don't see. I already did a couple of search in Google, but I haven't seen everything that shows up is for controlling the width that you insert with the image EMG command or thing like that. And via Markdown or via HTML, but you already imported the figure that exists. This one is one that it generates. Well, GMT generates and it reads and puts it here on the or the browser or this one. And it's when I don't have a way of controlling it, but must be something.
Yeah, I'll look into that. I think it seems like we do it a little bit differently, but I imagine there's probably some cell magic that you can use for automatically.
This has a lot of parameters controlled in the JSON files. I've looked, but I didn't find anything.
Yeah, it's interesting.
All right, I guess we should descend into the breakout room. So I guess we do have a seismology room, maybe, that we will pretend to be seismologists inside.
Yeah.
Yes. Joachim is our seismologist. He showed a beach ball most recently, so that
Yeah.
makes him a seismologist.
But it's stupid, that bug, because I fixed, but was with another
know.
data convention, not with the Aki Richard. So, and the number of columns is different, and something is failing on that patch. That is, it failed here again. So I was obliged to save the file and this to work.
We'll figure out when I have a weekend that has not completely been spoken for. All right. So, Lisa, are you ready to rock and roll? Okay.
Everybody should be allowed to pick their own rooms.
All right. See you on the other side.
Okay, I think we have everyone back from the breakout groups. This is the end of the short course, so thanks a lot for sticking around with us throughout the entire thing. We've enjoyed working with you and hope you've gained some knowledge from this. I think at some point you will receive a survey for feedback. We want to improve every year, so please consider filling that out when you receive it. The only other reminders are to submit your final products in the final products channel on Slack and to stay in touch through the GMT forum. So thanks everyone for joining, and I hope you have a great rest of your Thursday or Friday, depending on where you are.